Okay, thank you for introduction. Abigail, can you hear us well?
Yes, I can.
Okay, thanks. So we will tell a few words about our conference contribution, 4 seconds over South Africa. And it's about design, calibration, and launch and data processing of sounding rocket payload to measure the Earth's magnetic field. At the beginning, I will introduce a little bit the idea or what we have done. In the beginning of this year, we get an information that it will be possible to launch one unit CubeSat format payload on sounding rocket in South Africa. And it was for me interesting because currently I'm developing magnetometer for space mission Helvice 2, and it would be nice to increase its technology readiness level. So it was a nice opportunity. So until March, I have prepared the flight hardware, the logging unit for the main instrument, the AMR magnetometer. It was collecting data from multiple sensors, mainly the AMR magnetometer and also accelerometer and gyroscope, and 2 auxiliary magnetometers, temperature and battery voltage. The logging was performed on 2 redundant memories, the flash chips and SD card, to have a better probability of data recovery after we get the device back. But that did not happen. I will tell later. I also added a possibility for remote telemetry via XB, and it was just for debugging purposes, but later it's shown to be a very important feature. Here is a photo and slide about the main magnetometer. This is just a development model. It's not actual flight hardware for the space mission. And it's low noise radiation tested AMR-based magnetometer. And because we expected there will be some magnetic gradient and noise from other payloads on the rocket, we add also 2 auxiliary magnetometers on board of Logger to have any chance to denoise the data later. And now about a little bit about second most important feature of Logger, and that's start of trigger or trigger to start the data logging, because there is possible situation that it will be false positively triggered, and we will drain our batteries or fill our memories, so we get no data later. And also there is possibility of negative false trigger, so we don't have any data at all. So there were multiple triggers, one mechanical 2G switch, and integrated accelerometer, and temperature below 10 degrees Celsius, and manual XB command to start logging. There is a little funny story about 2G mechanical switch, because when we tested if it will switch properly on a rotation platform, I don't know if it can, oh, it can't be, it's video, but it doesn't matter. We mounted firstly the sensor on board correctly, as in the picture from datasheet, but when we tested with the rotation platform, it didn't switch. But we somehow missed the point that the acceleration on the rotation platform is on opposite direction than when the rocket launched. So this switch didn't work. Hopefully we had the integrated accelerometer which switched the trigger. Here is also a photo from calibration. All 3 magnetometers has been calibrated in 3 axial coil system. And accelerometer and gyroscopes were only tested if they works, as well as logging on SD card and flash. Now, few photos from testing of telemetry. Here in the middle is a picture with Dr. Janošek performing range test, approximately 300 meters. And also his notes from a launch pad, where we 3 hours before flight obtained information that it will not fall down with parachute, so we don't have any access to memories. We have only possible data from telemetry. So it was a little bit sad, but we updated new firmware on the launch pad to obtain even a few points of data. And here is everything we get. I think it's 30 lines of data from all sensors, and then the rocket gets out of our range. So now I will pass the word to Abigail to tell a few words about data processing.
Greetings. Can you hear me?
Yes.
So as David mentioned, we only got 4 seconds worth of data. This is the data from the gyroscope, which shows the angular velocity. As you can see, the rocket only started rotating at about 0.5 seconds, and it was rotating at about 2 revolutions per second after the 4 seconds. It was only rotating on the z-axis, because in the first 4 seconds, I doubt it was tilted in the x and y directions. Hence, it remains constant at 0. And then on the next slide, we see data from the accelerometer, the acceleration. So what happened was the place where we launched the rocket, they had their own cameras to record the motion of the rocket. So they gave us their data file, which consisted of the velocity, the time, and the distance of the rocket for the entire flight. So we had to calculate the acceleration for the first 4 seconds using that file, which is the blue curve. And then the orange one is the acceleration from our own accelerometer on the instrument. So as you can see, at more than 60.5 seconds of the day, the data corresponds quite well. But at the beginning, there's a lot of differences. I think it's because, as I said, the launch place had different cameras to capture the rocket's flight. So I think the rocket was moving from one camera to another, and that is what caused most of the disturbances you see on the plot. And then the next plot shows, this is just the raw data from the main magnetometer without taking into consideration any direction or any other factors. It's just raw data from the main magnetometer. But we couldn't really say much from this, so we had to take into consideration the angle of rotation. We had to take into consideration the direction. So what happened here was that I had to find theta, which is the angle of rotation. If we only considered theta for every 0.5 seconds, we would lose track of a lot of rotations. So firstly, we integrated the angular velocity data and interpolated it to every millisecond, and then resampled that to get the angles of the points that correspond to the timestamp on the instrument. So the blue curve shows the interpolated data, and then the red dots are the actual telemetry. And with that, with the angle of rotation, we were able to construct the vectors Bx and By, the magnetic field on the X and Y axis. Excuse me. The magnetic field on the X and Y axis using the theta, which is the stars, the green and red stars. And as we can see, they fit perfectly on the sinusoidal functions, which shows that the calculated theta was quite accurate. Yes, that's what we have so far from the analysis of the data. And these are some of the acknowledgements. We would like to thank Dr. Michael for his guidance and the instrument design and calibration, the SANSA team for the calibration and the launch support, and NRF and SANSA for financial support, and also acknowledge that this work was supported by the grant agency. And next is a picture without David of the SANSA team that is calibrating the instrument. Thank you.
Thank you, Abigail. Thank you, David. We have time for questions.
Okay, thank you for your presentation. I have maybe two questions. I will start with Abigail, please. If you come back to, yes, this slide, how did you interpolate this data? What was the tool, how you selected this function, or how you did it?
So firstly, I calculated theta from the data of the angular velocity on the previous slide. The angular velocity is, I used that, I calculated a nominal vector t and omega, and that was my theta to find the field on the x and y direction, to find bx and by, and those are the green and red stars. And then I fitted a cosine and sine function using the calculated theta.
Okay, thank you. And yeah.
The rocket is spinning in one direction, so it's expected that the horizontal components will commute over the time.
Yeah. And the second question, you have only 4 seconds of data. So it was an accident, of course, it's part of life. And but you said that you must have several trivial ways to avoid the battery discharge, or why don't you just select bigger battery or bigger storage for data?
Because it was expected that the rocket will be on launch pad for some days before launch. So the batteries, if the logging were the whole time, the batteries need to be very, very big and heavy. And we have some constraints about mass.
Okay, yeah, thank you.
Any more questions?